Okay, welcome to the second lecture on advanced control systems. In this lecture, we are going to talk about necessary and sufficient conditions for arbitrary pole placement. In the last lecture, we saw that a feedback law u is equal to minus kx helped us in putting the closed loop poles of the system at arbitrary locations. So the locations were in our control. Why? Because we could control the we could change the characteristic equation of the plant that we were trying to control. So we controlled or changed the characteristic equation of the plant that we were trying to control. So this is why state feedback is also called arbitrary pole placement. In this lecture, we are going to talk about necessary and sufficient conditions for arbitrary pole placement. But before that, we'll be taking a small example to show how powerful this method is to control any plant. So let us assume that we have an unstable plant. As you know, an unstable plant would have poles on the right half of the S-plane. So let us imagine something like this. If this is our S-plane, this is our j omega axis, this is our sigma axis. Let us imagine that we have poles here, right? And an example of a plant which has poles here would be something like gs is equal to 5 divided by s square minus 2s plus 2. The characteristic equation for this plant is s square minus 2s plus 2 equal to 0. And if you solve this, you'll get two poles at 1 plus j and 1 minus j. So this is the plant. It's an unstable plant, and what our objective is to apply the state feedback law u is equal to minus kx and stabilize it. If you look at the behavior of this plant for a step input, this kind of an input, it would respond with an oscillatory unstable response like this. Let us now assume that we basically want the pole location to be shifted to the left half plane, both the poles at the same place. So that's why we have a double cross. And suppose the new pole location is such that we want it to be equal to s equal to minus 1, minus 1. So both the poles in the left half plane and both of them equal to minus 1, minus 1. So how would we use state feedback law to do this? Now, if you look at this plant, what we can do is to write down the state space representation of this plant. So if you have gs equal to 5 divided by s square minus 2s plus 2, you can quickly write down the state space representation in the controllable canonical form as this: a is equal to 0, 1, and then you have this minus 2 coming here and this 2 coming here with a minus sign. B, as usual, is going to be 0, 1, all zeros, the last part 1, and C is going to be what you have in the numerator. So in the numerator, this is 5, and then all the other entries are 0. So 5, 0 is your C. Now, the new characteristic equation that you want is given by, so let me write the new characteristic equation. New characteristic equation should be such that s plus 1 whole square equal to 0. So how would you do this? Now, in this system, if you apply the control law u is equal to minus kx, you remember that the new state space representation of the plant becomes x dot is equal to a minus bkx. So if you write this as x dot is equal to a minus bkx, you have a minus bk equal to 0, 1 minus 2 minus k1, 2 minus k2, because k would be k1, k2, and bk would be 0, 0, k1, k2. So what you're doing when you're doing a minus bk is just subtracting from this a, bk. So you have this. Now how would the characteristic equation change? How would the characteristic equation change after you have applied the state feedback law, after u is equal to minus kx is applied on the plant? So we already know that the characteristic equation is given by, for this plant, which is x dot is equal to a minus bkx, would be given by the determinant of si minus a minus bk. The characteristic equation is actually the denominator of the transfer function, and in the denominator of the transfer function you have si minus a, the determinant of si minus a. In this case, a is equal to a minus bk, so the characteristic equation is going to be the determinant of si minus a minus bk. So what you have to do is to find out the determinant of this matrix that we have here. Now this is not very difficult to do. Still, I'll do this here. Si minus a minus bk would be, now look at this. So you have s minus this and s minus this here. So you have s here, and then you have s minus 2 plus k2, and then you have minus in here and minus here. So you have minus 1 here and 2 plus k1 here. So this is your si minus a minus bk. And if you want to find the determinant for this, so just look at this. This is going to be s into s minus 2 plus k2 plus 2 plus k1, which is equal to s square plus k2 minus 2 into s plus k1 plus 2. So the system now would have this characteristic equation. Now it's very simple to see that if you compare your original characteristic equation, which was this s square minus 2s plus 2, if you just compare this s square minus 2s plus 2 and you compare this with the new characteristic equation that you have got after you have applied the state feedback law, you can get the values of k1 and k2. So just by comparing these two, we can see that k2 minus 2 has to be equal to minus 2, which means that k2 would be equal to, just a second. So is there something wrong in this? K2 minus 2 s square plus k2 minus 2s plus k1 plus 2. Okay, sorry, you don't have to compare it with the original characteristic equation. You have to compare it with the desired characteristic equation. So the desired characteristic equation is s plus 1 whole square, which is equal to s square plus 2s plus 1. So now we can compare k2 minus 2 is equal to 2 and k1 plus 2 equal to 1. So you get k2 is equal to 4 and k1 is equal to minus 1. So the state feedback law, which will place the poles at the right location, would be given by u is equal to minus kx, where k is equal to k1, k2, and that is equal to minus 1, 4. Now we have obtained this result, by comparing the characteristic equations of the original system and the system original system with the state feedback applied, which is this, and the required characteristic equation, which is this. So this procedure becomes slightly cumbersome if our system size is large. What we did on the last turn was much simpler. We found out a formula for just finding the state feedback matrix if the system is in controllable canonical form. And the formula was that if your actual characteristic equation is s square plus a1s plus a0 equal to 0, and this is your actual characteristic equation, and your desired characteristic equation is s square plus alpha 1 s plus alpha 0 equal to 0. So this is your desired. Then your k1 is alpha 0 minus a0, and your k2 is alpha 1 minus a1. This we did in lecture 1. So if you apply this formula here again, so your actual characteristic equation in this case was s square minus 2s plus 2 equal to 0, and the desired characteristic equation was s square plus 2s plus 1 equal to 0. And you can see that your k1 is alpha 0 minus a0, so 1 minus 2, that is minus 1, and your k2 is 2 minus 2, so your k2 is 2 minus minus 2 equal to 4. So your k is k1 k2, which is minus 1 4. So getting the same result here and here, right? So what I basically wanted to tell you in this is that comparing the characteristic equation is another way to solve the same problem. Now in the second part of this lecture, we'll see what and how and when can you do this. Can you do this for all systems? Can you do arbitrary pole placement always, right? Actually, we'll derive a condition for necessary and sufficient conditions for arbitrary pole placement. So what is the condition what are the necessary and what are the sufficient conditions to arbitrarily place the closed loop poles of a system? Place the poles of a plant, right? So this is going to be the second part of this lecture. Thank you.